Today we're going to cover the bisection method, which is a technique for finding roots. And let's go ahead and get started with it. So let's say that we had used our incremental search function that we built yesterday, and we zeroed in on this root right here. Okay. And let's say that we found that some left endpoint, maybe being, I'm going to scoot this in here, say right here. And then let's say we have some right endpoint over here. And actually, I'm going to call that, instead of right endpoint, I'm going to call it X upper. So XU. And I'll call this one over here XL for X lower. Okay. And is what we'll do with those two is we'll choose a point right in the middle, and we'll call this XR. Okay. And so XR for root. Okay. So is what we're saying is hey, we think that this root is just somewhere in between here. Okay. And is what you can see is the actual root is a little bit to the left. So is what we do is this would become the new XU. Okay. Let me maybe grab a different color here for our next iteration. So this is iteration 1 of the algorithm. So moving on to the next iteration, this would stay as X lower, and XR is going to become our new X upper. Go. Yeah, let me actually erase that. That didn't look very good. So again, X lower, X upper, and I'm going to connect those, and we're going to go directly in between them. Okay. So our new XR is going to be right here. And actually you can see that that looks like it's a little bit to the left of the root, right? So for our next iteration, okay, this XR is going to become our X lower. Okay. I'll use a different color here again. So XR. Okay. So again, this is going to become our new X lower. Okay. And then you can see that our X upper will stay as it is, and we'll connect those. And so again, this is XL now, this is XU, and then we'll have our root in here. Okay. And you can see if we keep doing this process, we're going to get closer and closer to that root. Now the one question you might have is, you know, how do we determine which one's going to be the lower and upper without looking at the graph, right? Because we're going to have the computer doing this. We don't want to have to visually go in every time and look and see, hey, is the, you know, we don't want to have to determine that ourselves every time. We want to have some way for the computer to be able to do it. All right, here's how we're going to do it. Okay, we're going to make the same calculation before we move on to the next iteration every time. And so let's see what that calculation is. It's going to be f of x sub l times f of x sub r. Okay. And I'll just go ahead and write that next to each one of our iterations here, because we're going to have to do this. And I want to point out this same demonstration that I'm about to do here for this increasing function. You could test it out on a decreasing function, and you'd see that this all still holds. Okay. So if we were to look at f of x lower, you'd see that that is some negative value here. Maybe I'll, right? Some negative value. And then if we were to check f of x sub r, you can see if you were to just go up on the graph here, that put us somewhere in this region. Okay, so that's positive. So if you do a negative times a positive, you get a negative, okay, which indicates that over this interval here, there was a sign change, which means the root is in between xl and xr, which means that for our next iteration, we're going to assign x upper. Let me actually write the x in there though. X upper is going to be equal to xr. Okay, so we've updated x upper. Okay, and then we'll move on to the next one. Okay, and so moving on to this pink one that we have here, if we were to check this same thing, okay, we'll see that f of x sub l is still going to result in a negative number, and f of x sub r, if you're really careful and go up here, you're going to see that this point that I have here is just a smidge to the left of our root. So it's also going to result in a negative. So you have a negative times a negative, which is a positive. Okay. So this means that there was no sign change in between these two, and that our root is actually in here. Okay. So that would mean that we'd want to assign x lower to equal xr. Okay. Let me see if I can get rid of that. Yeah. And then finally, for the last one, if we were to want to do one more here, it looks like my xr is a little bit to the right of the actual root, so this will be positive, and x upper, if I plug that into the function, will also be positive. So again, there was no sign change, which means that the root must be in this interval. Okay. So that would mean that we would want to assign x upper to now equal xr. Okay. Now, the one thing I didn't talk about how to calculate here, which is important, is how do we get xr? Well, I said it's directly in between x lower and x upper, so we're always going to find that by doing just the average of x lower and x upper. Okay. And this is really all we need in order to implement this algorithm in MATLAB. So that's what we're going to do next, is we're going to switch over to MATLAB and try this out. Okay. Now that we're in MATLAB, is what we want to do is create that bisection function that we were talking about in OneNote. And so you can see I already have it saved as bisect, and you can see that the function name matches that, okay, which is good. And then let's look at our input. So our input will be some function. Okay. We're going to need an x lower and an x upper, right? And so is what we want is we want our root to be somewhere in between those two. ES, this is the desired relative error. Okay. And as you can see down here, we'll code in that if you don't input ES, the desired relative error, is what we'll do as a default is we'll set that to 0.0001%. Okay. The next thing is the maximum number of iterations. So basically, if we, if our code's taking a long time to run, maybe there's a point where we just want to say good enough. And so that's what's going on here with maximum number of iterations, is we're saying by default 50 is enough. If you would like more, you can set that at some other value, okay, or less. Okay, and then var argin, this is something that we haven't seen in a function yet, and this is going to allow for actually additional inputs. So this stands for variable number of arguments, or input arguments, and we'll see how that works when we actually go to use the function, okay, because we will actually use our bisect function that we're creating here once we're done with it. Okay. All right, now let's go down here and get started. So the way that we're going to start off most of these is just thinking about the inputs. After that, we'll actually get into bisection. Okay. So to start this off, we're going to say if nargen, so if the number of input arguments is less than 3, we have a problem, okay, is what we're going to say. We want to have at least these 3 inputs. We can set these other ones as default, okay, but we want to have at least these first 3. Okay. So if there are less than 3, is what we're going to do is we're going to display an error. Okay. Remember, we need quotes around our words here. So at least 3 input arguments required. And remember, we can do this all in one line, this if statement here, if we just separate each part by a comma. So there's my end, but we need to spell it right. There we go. Now, there's another thing that we can actually build in here. So if I were to actually maybe go back to OneNote for just a second, okay, let's say that we had started this off and we picked our XL and our X upper, and actually there was no sign change in between XL and XU. Well, that would be bad, because if there's no sign change in between those two, that means that there's no root in between. Okay, so if we actually plug in XL and XU into our function, okay, multiply them, if we get a positive, right, that means that there was no sign change, and we chose badly. And if it's a negative number, then we know that there was a sign change. Okay. So that's what we're going to build into this next. Okay, essentially another check for an error. So I'm going to say test equals func. Okay, right, up here we said that one of our inputs is going to be a function. So func. And the next piece here is we wanted to plug in XL. Okay. And we do have to be careful. If I type in 1 and if I type in L, they look very similar. The only difference is the 1, the top of it is angled downward, as opposed to the L, the top of it is straight. Okay. And so I frequently type in the wrong one. So I'm reminding you of this so that you can kind of be careful here. All right, and then we want to multiply by func of XR, or sorry, not XR, X upper. Okay, and this should do the trick here as far as what we want to calculate. But that var argin that we had up there, again, is going to allow for a variable number of inputs, and that variable number of inputs has to do with this func that we're talking about here. And so to actually implement that var argin up there, we want var argin, and we want the curly brackets with this colon here. Okay. And this is just saying that the rest of our extra inputs that we might have here, they're going to go into this function. Okay. If I just wanted say the first one, the first extra input to go into this first calculation here, you know, I could say var argin 1. This would just pull that first extra input and plug it here. Okay. But we want them all to go into this function. Okay. And same with here. Okay. Okay, so there's that. And now, what is it about this test that we said would be bad? We said if there is no sign change, this would be bad. And so no sign change would be associated with getting a positive number, right? Because that would mean we're doing a negative times a negative or a positive times a positive. So if this thing is greater than 0, we have a problem, okay? And so I'm going to go ahead and suppress this. Oh, actually, I don't want the greater than there. I'm going to suppress this value for test, and we're going to write ourselves a little if statement. So if test is greater than 0, okay, what do we want to happen? We want to say, hey, there's an error. Okay. And that error is there was no sign change. And then comma end. Okay. And if this test value is less than 0, then we don't have any issues, and so we'll move on to the next spot here. So if nargan is less than 4, okay, or, okay, and we'll explain that in a second, but remember the vertical bar is or, is empty. Okay, so you can remember that little function that we have here. And is what we're going to say is empty is ES here. And so if nargan is less than 4, or we haven't input anything for ES, is what we're going to do is we're going to say, hey, ES is equal to 0.0001. Okay. And then we can just go ahead and end that. And you can see I suppressed the value. I don't want it to output ES here. So I'd like to explain why we needed this OR situation in here. And so here's the idea. Okay. We don't have the function finished yet, so I can't actually run what I'm about to do. But let's say we put in our function. We put in our x lower, our x upper, so we're saying that there's some root in between 1 and 5. We don't know exactly where, but it's somewhere in between there. We could actually put a comma and then leave ES blank. So write in another comma and then go on and fill in the next part, which would be the maximum number of iterations, so say 100. Okay. So all this is empty is doing here is saying if there was nothing here, then we're in this case. Okay. That's all that's going on there. All right, so now the question is, well, what if nargan's less than 5? Okay. So if nargan is less than 5, okay, or is empty, max it. Okay. So this is doing the same thing. It's saying, hey, if we have less than 5 inputs, or we've decided to just leave max it blank here, then is what we'll do is we're going to have to set max it to be something. So max it is equal to 50, and we'll suppress that and end. Okay. All right, and now we can start moving on to our actual bisection function. This is just all the bells and whistles that we've done up here. Okay. The first thing that we'll do from here is we are going to start our while loop. Okay. But we're going to actually have a different structure than we've ever had before. Okay, you might have read about this in the text, but the way that this is going to work is we're going to say while 1, and essentially is what this is going to do is this is going to run no matter what, and the only thing that's going to stop this while loop is going to be, we're going to say if something happens, break. Okay, but we'll need to fill that in later. Okay, so for now it's just while and then 1 in parentheses, and again this is just going to ensure that this runs no matter what. Okay, because you might remember that before a lot of our while loops we often had to introduce a lot of things in order to get it to work. Okay, we will still have to introduce some things above the while loop, but not as many as in the past with this new structure. Okay. So the next thing that we might want, okay, and we're going to have, maybe I'll put in a few notes here for us. There's going to be some stuff here, but it's not intuitive why it's going to go there yet. There will be something that'll go here eventually, not intuitive why yet. Okay. But the one thing you do know is if you wanted to compute XR, that would be equal to the X lower plus the X upper divided by 2, right? We said that that was going to be the average. Okay. Another thing we want to do, right, is we have that maxit function going. Okay, and I shouldn't call it a function. We have maxit as part of our function, maximum number of iterations. Well, why don't we go ahead and just say, well, iter is equal to iter plus 1. Okay. But if we want to do that, we need to let MATLAB know what iter is. Okay, so iter equals 0 to begin with, right? If the while loop hasn't run, we've done no iterations. Okay. And I'm going to leave these in here because even more is to come. Let's look at the next piece here. So another thing we'd like to do is we'd like to be computing that relative error as we go. Okay, so I'm going to say if, and I'm going to have EA is equal to the absolute value, okay, and we're going to have our XR, so our approximation of the root minus actually our XR old divided by XR, okay, and multiplied by 100 to convert this to a percentage. Okay, and then I'm going to say end. Okay. And you might be wondering, why did you write an if and an end here? That seems completely unnecessary. Okay, and so here's why. What if our XR is equal to 0? Then this is going to be undefined, and this is going to cause us some issues. So as what I'm going to write before this is if XR is not equal to 0, oops, that's an O. Okay. If it is not equal to 0, then we'll go ahead and we'll compute the error. We're going to suppress it, and then we'll end this. Okay. So that's what's going on there. That's why I included the if. Okay. And then next, you might remember that when we were looking in OneNote, we were doing something very, very similar to this up here to determine whether we had a sign change, except for it was XL minus XR. Okay, and so we're going to make sure to include that. Why don't we just go ahead and copy and paste this? Okay, so right below here. And the next thing I'm going to do is just change this XU to an XR, just like we said. Okay. This is telling us if we have that sign change, and remember, this broke us down into 2 cases. Okay. If there was a sign change, we did something. If there wasn't, we did something else. But I want to point out something else before we move on here. So a couple things. One of them is, well, we haven't given an XR old anywhere up here, so it's not going to know what to do when it runs into this situation. Okay. So we will need to define that. Okay. And what we'll want is as we do run this, we'll want to say, hey, XR old, just make that equal to literally the old XR. Okay. We're assigning XR old to equal XR every time we run through this. Okay. But then we have another issue. Our calculation of XR is down here. Okay. So a quick fix to this is you could just say XR equals XL. Okay. And this will just get things moving. Okay. And then after that, also you might notice, actually, we don't see this yet, so I'm going to leave that out. We might add one more thing here. Okay. All right, and then after our test, we do want to build in those cases. So if test is less than 0, what do we want to do? Okay. So remember, if the test is less than 0, that means that we have had a sign change. Okay. Maybe I can pull our OneNote back up. Okay. So when we have had a sign change, remember that was an indicator that our root is actually in between here and here, okay? Which means that you would want to make your x upper become xr for your next iteration. And so that's what we're going to write in here. Okay? So let me switch back to MATLAB. Okay? So I'm going to write in here that x upper is equal to xr. Okay? I'm going to go ahead and suppress that. Then there's another case. Okay? If else if is one word. If this test is greater than 0, that indicates that there is no sign change, and so we'd want to do the opposite. We'd want to say x lower is going to equal xr. Okay? And so that looks good. Now, there is actually one other situation. Okay? Well, what if the test is 0? Okay? Well, then that would mean that our error is actually 0. Okay, and so let's go ahead and end this right here. Let's see. Maybe I'll put in a little bit of space here too, so you can just kind of see that this is all one chunk here. All right, this is us just assigning xr to either x upper or x lower, so that way we can move on to the next iteration here. And you can see this if statement already has its end. This if statement has its end. Our while loop still doesn't have an end in there, but we will get that there here eventually. But I'd like to point out something else. Well, if xr is actually equal to 0, okay, to begin with, right, we couldn't compute EA here. And the way that we're going to break this loop is we're going to break it by saying that the error or the maximum number of iterations has reached some point here. Okay. Well, if we were unable to actually compute the error, then we might not be able to break things. So we might want to be able to come in here and actually say up top, where is it? Here they are. That EA is just equal to something. And we'll make it something that's way larger than what ES is, right? ES is the desired relative error. Let's just say 100% error. That's huge error. And this will just ensure that everything works. Okay? We're going to need it for this next part. Okay? So I'm going to have in here if EA is less than or equal to ES. Okay, so if our relative error is less than our desired relative error, okay, we can stop this while loop is what we're going to write here. But remember, we also have another stopping point potentially is our maximum number of iterations. So if our number of iterations has exceeded or is equal to max it, then we will break this. Okay, and the last thing I need here is an end. Okay. So there's an end for that if statement, and then we can actually finally write in an end for the while loop. Okay. But remember, this is new, what we've done here. This while loop is going to keep running and running and running and running until one of these two conditions is met here. Okay. And so the last thing that we actually need to do is we would like to put in what we, want those outputs to be. Remember, we said up here one of the outputs is root, and we haven't defined root anywhere. Okay. Well, root should be equal to xr, right? That's what xr is it's our approximation of the root. And another interesting output to have here is fx. This is the function value. So this should always be very close to 0. If it's not close to 0, we didn't come up with a very good approximation. So fx is equal to func of xr. And then again, we may have a variable number of input arguments. So var argin. And that ends our function that we just created here. And is what I'd like us to do is go back to that bungee example we were doing yesterday and test out our function, but we should save this first. All right, now that we're looking at our bungee example, we can see that we pretty much have in here what we had yesterday. I'm going to have us run this incremental search here one more time, and maybe have it output those brackets so that we can see what they were again. Okay. So we can see that this root is somewhere in between 140 and 140, or about 140.8 and 142.8, somewhere in between there. Okay. So we could use these in our bisect function as our lower and upper bounds. Okay. So that'll be nice. But inc search, I want to point out, can only take in one input for func, and that is m. Okay. But we're a little more creative with our bisect function. We allowed it to actually input multiple extra inputs for func, using that var argin command. Okay, and what we're going to do here is I'm actually going to get rid of the inc search here. That way, when I go to use my bisect function, I don't run into any issues with this program being mad about the incremental search, because it will be mad about the incremental search because I'm going to make some edits here. Okay? But I want to go up here first and show you all a nice little trick. So we've been clearing all, but we could do clear vars except xb, because we want to keep those values. We're going to plug those into our bisect function. Let's go ahead and we're going to hit run just to make sure that it does not clear xb. And you can see over here we have not cleared xb. Okay. Or we could have just avoided hitting clear all in the first place. So the next thing that we're going to do here now is we are going to actually change this function a little bit. Okay. We're going to change it so that it actually depends on multiple variables, but I'm actually going to save that for here in a few. Okay. Let's just go ahead and use bisect to begin with. So we have bisect. We would like the function. We would like to have our x lower and x upper, which are contained in the vector xb. Okay. And then if we wanted to, for instance, we could leave the desired relative error empty, just using brackets like this. And then we could say, hey, we want the maximum iterations to be 100. Okay. And so we could hit run. Okay. See what bisect tells us. Okay. It's telling us that the root is about 142.7377. Okay. Well, let's try to invoke the power of var argin here. Okay. I could change this down here to be m, g, c sub d, and t. Okay. And so you can see that I have g, c, and t here, but what I could do is I could actually plug these in over here. This is what that var argin is for, is I can say, hey, now I'm going to plug in the remaining variables, right? Because it's going to plug in stuff for m already. But for these remaining variables, let's plug in 9.81. Let's plug in 0.25. And you have to do this in order, right? So you can see I did, let me explain what I mean by in order. I mean that I have to do G, and then C sub D, and then T. Okay. So we have T equals 4. Okay. And I'm going to get rid of these just to show that, var argin is doing what it's supposed to be doing here. Okay. And also, it will hopefully clear out some of these other things because we already have G and T and all that stuff stored here. So I'm going to go ahead and hit run. And so you can see that this is still working. Okay? This is still working. It's plugging this in for G, it's plugging this in for the drag coefficient, and it's plugging in T. Okay, but we still have some more options with our function here. Let's say we want it to output all this stuff right here. The root, the function value, the relative error that we ended up with, and say the number of iterations. We can do that. We can put this here, and we can go ahead and we can run. Okay, and if this worked right, this fx here is the function value at our approximate root. So if our root that we found, or our approximate root, is decent, then fx should be really close to 0. And if I scroll up, you can see it indeed is very close to 0. Okay? It's 0 point, and then 5 more zeros, and then 1, 1, 2, 9, 7. That's pretty close to 0. All right, and that is going to be it for our bisect function.